Hey, nice that you're back. Today we will look a bit into generics and traits, and I think it's a very interesting thing to learn in Rust because you can really do so much with traits, and it works a little bit different than in C++. So let's get going. There's a lot to learn. We will start with a basic structure that just owns some data. So we have a value. For now we can say it's F32, and then we can implement a test. We call it test generic and just see how we can initialize this. So as we don't have a new function, we can just create it like this, value equals 1 for the beginning, and store it in data. So now you see our data object is always with an F32 inside. But if we want to change this, because we don't know yet what the value will be, in audio, for example, you will most often use F64 or F32. So you want to enable that the object works on both types, or maybe you even have more values you want to store in there. So what can we do? First, we have to create a new name for our type that is not known yet. Most of the times we use T. And then you also need to make it known here. So this is what you have to do. Like here, we specify the name of our type, and then we can use it inside. And then you see already in the test, now this is data F64. So by here, it's really baked into the type and has no runtime overhead or something else. So if we create another data type and we store an integer, you will see that those are just two distinct types now. But with a nice interface, because we don't have to write things a lot of times, right? And because T has no bounds whatsoever, it can be any type. It can also be something larger, like a string. Let's just store hello in here. All right, so you see now we have data string. Now if we want to implement some functions for the struct, there is this implementation block. You could choose now to have a specialization, so an implementation block that is only for one of those. For example, we start with F64. And here we can create a function like just a simple getter. We need a reference to self to access our member variables, and then we return our F64 value. Because by here, we specified that we guarantee that the T is an F64. So we are returning an F64. And then we can just call self.value. And you see self.value is F64 here. Now, it's possible to call this get function here. And maybe let's assert equal data.get is actually 1.0. Yeah. Let's run the test. All right, that works. And now we could just do those implementation blocks for all the different types we have. So now we could use I32. Yeah. And you will see that the get function is also existing for I32 now, because those are just different types, right? So let's change it to this. All right, that works. This is very efficient. I mean, by here, you can do all the math operations that are existing for F64. We know exactly which type it is, but it's a little bit of work writing all of this, right? So there's another option, and this is where this first thing here comes in. So we can, again, create a type. Yeah, this can have the value T like above, but we can also call it different, for example, F. And then we can use it here and here. So this value really just says which names you want to use. Here we say which of those it should fulfill, so we can have multiple here, right? So we set them here. and then we can use it inside of the block. So this still doesn't work though, because our member variable would be moved here. So it would be moved out of our structure, and this is not allowed in Rust. Rust always moves stuff by default. So here we see cannot move out of self, which is behind a shared reference. What we could do though is to say self is moved inside of here. So then our function works again, yeah? Let's call it. And it works. And this even works for our string. Yeah, let's compare this. Call it again. So that's no problem. Now everything gets moved. It's performant. Moving is also real-time safe. Should be. This is not a big problem, yeah? But afterwards, we cannot use our data object anymore, right? If we call data get again, you will see used of moved value data. It doesn't exist anymore. So that's why we have a shared reference here. But now it needs to implement clone or copy so that we can get this value outside of our function. Yeah, obviously another option would be just to get a reference. This works. Now we just need to call it like this, yeah, and that works. But another option is to specify a trait bound. So we say our f should not be any type, but a type that has a certain functionality. So we can add, for example, clone here. And clone is a trait, so that's the functionality I was talking about. And what is a trait? It's just this sort of contract, what our structure is able to do. And inside of here we see which functions are implemented on those types. So we have the function clone and the function clone from. Let's go back. So now our self.value has functionality. We see now all the functions that our trait bounds here have. We can call them. Yeah? So let's call clone, and now all of our tests things here run. All right, but cloning is not that real-time safe. I mean, it is for F64 and i32, but it isn't for string because it allocates new memory. And that's why there's something in Rust that is called copy. And if we click on copy, you see it's an empty trait. So it doesn't even have functionality. It only sort of inherits the functionality of clone. But it is more of a marker trait. So the compiler knows it can clone it implicitly because it's very, very cheap to do. So if we add copy to our trait bounds, we can remove this clone and it will still work because this clone basically gets called implicitly. And now we see it works for our numbers, but it doesn't work for our string anymore because a string is not easy or very, very cheap to clone. All right. So I hope you understood this a little bit, how the trait bounds work. And yeah, let's have a little bit more functionality. For example, we want to add a math function. It could be something like just add a number to it and return it. So we add another number that is also of type f, and we want to add it here and return it. So you see, now this doesn't work because cannot add f to f. Yeah, and you see here what the trait actually is. It's called add. So we can just specify it here with a plus. With a plus, we can just add more and more and more functionality. So let's use add. It still doesn't work because add also needs an output. This has just something to do with the trait implementation, because adding should also be possible when the output value is something else than the two input values. But in this case, we just want to say that the output is the same as the input. Let's close it here And now this add function works and compiles. If we go to the add trait, you see again how that's implemented. It's just this trait add with the right-hand side that is safe again as well. And then here's an undefined output type. And that's the reason, because here is no default equal. We need to specify this output. And then you see, other than that, there's just this add function that has a right-hand side. And we see that the alias is plus. The compiler can just call this add function when we write a plus. All right, so now let's just test it. Here we can say data add 2.0, and we can assert that this is 3. All right, this should work. We have to comment this. All right, that works. And it should also work for the 1. For the integer, as an integer is also addable. Yeah, add 2. And our test compiles and runs. Perfect. But now if we have, I don't know, a complex process function here where we have a lot of mathematical operations, it might not be as nice to put everything here, yeah, plus and plus and plus. So one option we have is to write it down there. It's just that that we have more space. So here's this where f implements this. Sorry. Yeah, you can specify it like this. You will see that sometimes. Or you have another option and create a new trait. So we can create our own trait here. Pub trait, we call it number, for example. And number should have all of those things. So let's remove this. So number should have copy and add. Yeah. Now we don't have f anywhere here, so we just call it self. And this will work. So this number trait can be used now here. And you see that it compiles. But there is still one problem. The test doesn't work because number is a trait we have here and it is addable, so we can use it here. But our value f64 and also i32, they don't implement it. They don't know of this type, of this trait. No one implemented for it. So we can either just specify it here and say implement number for f64. Yeah, let's see what it says. And now you see it works. And also implement number for i32. And now you see our test compiles again. Yoo-hoo! And it just works. But this might be a little annoying to just add it for all of the types. So there's also a little bit complicated looking but very practical line you can set here. And we can automatically set it for all types that have copy and add. So that's the magic we can do here. It looks a bit complicated, bear with me, but you just add this line once and it will automatically be implemented for all of the types. Let's see what we do here. As before, maybe I leave it in here. You see we implemented number for f64. And now we implement number for t. Yeah, t is our type we don't know yet. And we also have to make it known here. So it looks a bit like in here. Yeah, implement f data f. Here it's implement t number for t. And then we say where t implements and then all of those traits. Now we can remove this. And this works. Yeah, you saw this where already down here. So we could also specify it like this. Yeah. Oops, not the double T. Okay, this works as well. Implement T, which has those functionality. implement number for all of those t's. And you see it still compiles. And our test works. Great. So this is really how you do it. Yeah, we could also call it float and add some more functionality that only float has, for example. But if you don't like to do that, you can also use a library. There are some libraries that implement that are doing this stuff for us already. So to make our lives a bit easier, we can just add cargo add num. Yeah, you can also just add num traits. That's the sub library of num, a sub crate. But we add the full number crate. You see it's adding num 043. If we go to our cargo toml, you see it again. Here's our number crate. And now there's stuff in num, for example, num. Or there is num float. Let's try it with float. And now we see float accepts an F64, but not our I32. Yeah, we can change this to F32 and then you see that it will work. So we can call it with F64 and F32 and our functions compile. So that's great. This num float makes it a bit easier, right? Let's have a look into what this actually is doing. It is not more than what we did here. Yeah. Let's go to float. You see it's a new trait. And it implements this num, copy, numcast, ordering. Ordering is just this smaller or larger than, and negation. And it also has some functions on it. For example, those. And the numcast is basically just that we can call from. So you can convert a t into a specific F32 or something like this. Or we can, just that we can use it together with F32s and F64s that are specific. All right. Yeah, I hope you learned a little bit and you're not that afraid anymore of those generics. Yeah, with this float crate, you have all the functionality you need here. Or you just want to stick to your own trait, if you don't want to use so many external libraries. But this number crate here, num, is a really, really common one. It's used in a lot of projects, so it's kind of, I would already see it as an extension of the standard library. But there are some weird things. For example, float does not implement debug. So if you want to debug our number, for example, save.value, it doesn't work. Yeah, that's a bit weird. But we can print it, I think. Let's see if it implements display. Yeah, no, it doesn't implement display. Yeah, so that's a bit unfortunate, but we could call to F32 on it and it still doesn't work. Why does it still not work? Yeah, okay. To F32 now works. It was an option. So we still have to unwrap it. Yeah. And then it also works without this. Just shortly, this means we call the display trait. It's also a trait like this. And the display trait means it's something that is meant for the user of our library. This here means we call the debug trait. And the debug means it's more meant for developers. It's not something that a user interacting with our program should see. And then there's also another thing like what is also in this debug. Yeah, this is the same. It's a debug print, but in a more extended, more beautiful way. And here I think you can call it like this or like this. Yeah. So this now creates like this. What debug prints, it can in some cases it spreads it out a little bit wider, so it's a bit easier to read. And this is a more compact print. So those are all the three printing types. But yeah, this doesn't implement debug. If you want that, you can just add it here, right? It is, it is standard FMT debug. Yeah, and now we can also print our value. But it's not necessary. You can always just call it to F32. All right. Thank you for watching and see you next time. Bye bye.